Hello guys, welcome back. This is the second video for the chapter motion, and in this video we're going to discuss graphs, especially distance time graph and speed time graphs. And before this video begins, I just wanted to tell you guys that the notes that I've made for motion and all the upcoming chapters are going to be available for free in the drive, and I'm going to be sharing the link for the drive in the video description. So if you want those resources, make sure to get them. So let's start. Okay, so the first thing that we're going to do is talk about distance time graphs. Distance time graphs are graphs in which we plot distance against time. We've got distance on the y-axis and time on the x-axis. Now here I've written an example so that we can properly understand how we plot distance time graphs. So the example says that Ali went to A from B in 5 seconds. So this is point A, this is point B, and Ali is a person who walked from point A to B in 5 seconds. He remained at rest at B for 2 seconds, and the third point says that lastly it took him 3 seconds to go from B to D. So he remained at rest, he remained at B for 2 seconds, and after that he went to D in 3 seconds, and the distance from B to D is 10 meters. So now we have to plot the distance time graph for Ali. Okay, so when the time is 0, Ali hasn't traveled anywhere. Ali is at A. Okay, then he goes to B. Now we know that B is 20 meters away. So on the distance axis we can see that 20 is here. And how much time did it take Ali to go to B? It took him 5 seconds. So we put our marker on 5, and then we use both of these values to find B. Okay, so I've plotted B here. Then we say that Ali remained at rest for 2 seconds, which means that Ali did not go anywhere, so his distance did not change. He remained at B for 2 seconds. So we see this flat line at B for 2 seconds. This is 6 and this is 7, so we get a flat line at B for 2 seconds. The last point says that it took him 3 seconds to go from B to D. Now we know that D is a further 10 meters away, so if he had traveled 20 meters before, this means that he will now have traveled 30 meters. And they've told us that this B to D travel was for 3 seconds, so we go a further 3 seconds ahead of 7, so 8, 9 and 10, and then we plot the point D. When we connect all these points, we get this graph, and this is the distance time graph for Ali. One thing to keep in mind for this graph is that the speed is always constant, which means that we assume that Ali is always moving at the same speed and like instantly. So like if he's at rest at point A, and when he starts to move for point B, he instantly starts to move with, for example, a speed of 10 meters per second. Okay, there is no acceleration and deceleration for this graph. So now we're going to talk about a scenario where we do consider the acceleration and deceleration of an object. So we've got this distance time graph here. I'm going to call this graph 2. Okay, so in this distance time graph we can see that there are curved lines, and we're going to discuss why these lines are curved and what do they represent. But just to give you a heads up, this is for the distance time graph in which we show acceleration and deceleration. Okay, so let's start. The point says that a car starts from rest, uniformly accelerates until reaching a constant speed. It then moves with a constant speed for some time, and then lastly it decelerates. Okay, so let's try to understand the first portion, A to B. The pointer below says from A to B the car accelerates as the line gets steeper. So let's try to understand why does the line get steeper when the car accelerates. Okay, so let's try and understand the connection of steepness of a line or a graph with its speed or velocity. So imagine that you've got two cars, okay? One of them is moving at 50 meters per second and the other is moving at 20 meters per second. Now the car A, which is moving at 50 meters per second, is going to travel 50 meters each second. So if we plot the graph for 1 second for car A, in 1 second it's going to travel 50 meters. Now for car B, if we do the same, the car is going to travel 20 meters in 1 second. So the point is going to be somewhere here. Now if we connect these points, the line for car B is going to be, it's going to be like this, and the line for car A is going to be much steeper like this. So with this we can see that as the velocity or speed of an object increases, the distance time graph gets steeper for that object. Now if we implement that concept in this graph, we can see that when this object starts to move, it isn't very steep. Like for example, this is very low gradient, but as time passes, the steepness or the gradient of the graph starts to increase. Okay, and this keeps on increases until we reach point V. So the car accelerates from A to B as the line gets steeper. From B to C we can see that the line is almost basically constant, or like it's a straight line. It's not getting any steeper. This means that the velocity or speed is constant. So from B to C, this is almost a very straight line, a patch. So this shows us that this speed is constant. Now from C to D we can see that the steepness starts to decrease. So if we closely look at it, the steepness is decreasing as the line is getting flatter and flatter. This shows us that the car is decelerating, or the speed is decreasing, or the velocity is decreasing for this car. Okay, so now let's do an example question so that we understand how we apply this concept in real life questions. So we've got a question that a train sets off from a station at time t is 0. The graph shows how the distance between the train and the station varies with time. So I'm gonna make this small diagram. We've got train and we've got station, and this is the distance that the graph is representing. Okay, so in the beginning we see that the train and the station are almost they're very close, which is why the distance between them is 0 here. Now the train starts to get away from the track, get away from the station, which is why the distance between them increases, and this continues till time t1, where the distance between the train and the station is maximum, and after that we can see that the distance between them starts to decrease again. So which statement about the movement of the train between t1 and t2 is correct? Okay, so let's start and look at it. The first option says that its speed is decreasing and it is moving away from the station. Now the first thing that we need to make sure is that to know that if the train is moving away from the station or towards the station. So if this is our station and this is our train, the distance between them would increase when the train is moving away from the station. Okay, and the distance between them will decrease when the train is moving towards the station. And we can see that from time t1 to t2 the overall distance has decreased, which means that the train is moving towards the station. With this we can cancel out A because it says moving away from the station, and C as well because it's also saying moving away from the station. Now the options that we are left with are B and D. The speed is decreasing or the speed is increasing. Now this is where the question gets a little bit tricky and where most of the people will start to get confused. So let's try and apply our concept of steepness of the graph with the speed. So for this question we can see that at time t1 we can say that the steepness of the graph is somewhere here, but as we get closer and closer towards time t2 we can see that the steepness has increased. Like if you look at this point, the graph was somewhere like here, and if we look at this point we can see that the graph steepness has become this. So we can see that the steepness has increased, the graph has become more slanted, and as the steepness of the graph increases, its speed also increases. Now this indicates that our correct answer is D. Okay, we've got another question that we can do. Which part of the distance time graph shows the fastest constant speed? Okay, so we need to look at the fastest constant speed and if we choose between these four parts of the graph. So let's look at the graph. Okay, so in part A we can see that the distance is increasing. In part B the distance is constant, it's not increasing or decreasing. In part C again we can see that the distance is increasing, and in part D we can see that the distance is constant. Okay, so now we have to figure out what do the flat lines and what do the slopes indicate. So in B and D we can see that the distance remains constant. Now the distance remains constant only in the case when an object is stationary, when the object is not moving, because if the object doesn't move, it's not going to cover any distance. So we can already cut out B and D. Why? Because they're asking for the fastest constant speed. Okay, and in B and D the object isn't moving at all. So now we're left with the option A and C. The only difference between A and C that we can look at it with our eyes is the steepness of the graph. So A is a bit less steep, B is a bit more steep. Okay, C is more steep and A is less steep. Now if we recall, we know that the steepness of the graph is directly linked to the speed of the object, because this example right here, we saw that A, which is represented using this line, is steeper, and B, which is represented using this line, is less steep. So as our speed or velocity increases, the steepness of the graph also increases. So if you're looking for the fastest constant speed, we can see that the gradient of the line C is higher, thus C is the correct answer. Okay, so the last part of the distance time graph is how we can calculate speed using the distance time graph. Okay, so we have to know that the unit of speed is meters per second or distance over time. Just keep that in mind because that will help us to build the concept. Now before we move on, we need to understand what the gradient is. We've talked plenty about this before, so it's gonna become much easier. That gradient is the steepness of the graph. Like line A is has higher steepness, has a higher slope, so it has higher gradient, while line B in this case is less steep, so it has less gradient. Now the formula that we use to calculate gradient is y2 minus y1 over x2 minus x1. So let's understand what do y2, y1, x2 and x1 represent. So the thing that we do is that we take a graph, okay, we take 2 points on that graph. So I've taken the two example points, point 1 and point 2, and each of these points will have an x and a y coordinate. So I've named the coordinates of point 1 x1 and y1, and I've named the coordinates of point 2 x2 and y2. Now I'm going to use these coordinates to calculate the gradient. I'm just going to simply put y2 here, y1 here, x2 here, and x1 here. And when I apply this formula, I'll see that I'm going to calculate the gradient. So for a distance time graph, we have to know that the gradient of the distance time graph is actually the speed. Okay, so I've got an example here that we can help to understand. So we've got this distance time graph, we've got distance on the y-axis and time on the x-axis, and now we have to calculate the gradient. So we know that gradient is y2 minus y1 over x2 minus x1. So I just plug in the values. I've plugged in 25 here, 10 here, 5 here and 2 here, and I've calculated, and my gradient comes out to be 5. Okay, let's not look at the units yet. I'm going to prove how this meters per second comes here, but our gradient is 5. Now we have to check if the units are indeed meters per second or not. So the formula for gradient is delta y over delta x, where delta y is y2 minus y1 and delta x is x2 minus x1. So if we look at the units of y, we can see on the y-axis we have distance, and the units of distance is meters. So we can put meters in the numerator here, and the unit of x-axis is time, and the unit of time is seconds. So I can put s in the denominator here. Now if we simplify, we can see that this also simplifies to become meters per second, and thus if we calculate the gradient of a distance time graph, we can get the speed of that object. Okay, moving on, let's talk about speed time graphs now. So I've got another example here that we can use to help understand how we can construct speed time graphs. So the car accelerates constantly from A to B to 20 meters per second in 3 seconds. So we've got a path here which has points A, B, C and D, and we've got a car on top of it, and it's moving on this path. The first point says that the car accelerates constantly from A to B to 20 meters per second in 3 seconds. So from A to B, the car accelerates from rest to a speed of 20 meters per second in 3 seconds. Then from B to C, it moves constantly with that velocity or speed for 5 seconds, and then from C to D it decelerates from 20 meters per second to 10 meters per second in 2 seconds. So now we have to plot the speed time graph for this car. Okay, so if you look at the first statement, the car was initially at rest at A. Now this is A, and we can see that the car was indeed at rest. Okay, I'm going to use a different color. Then it says that the car accelerates to 20 meters per second when it reaches B, and this all happened in 3 seconds. So if we look at it, this is 1, 2 and 3 seconds. The car accelerated to 20 meters per second, so we plot a point here and we label this B. Next it says that from B to C the car moves with the constant velocity and or speed for 5 seconds. So for 5 seconds the speed or velocity does not change. Okay, so let's add another 5 seconds into the 3 seconds we previously had. So 4, 5, 6, 7, 8, and as we know that the speed did not change, so this is going to be a flat line, so the speed is the same. And lastly it said that the car decelerated to 10 meters per second from C to D in 2 seconds. So in 2 seconds the car speed decreased from 20 to 10 meters per second. So if we were at 8 seconds before, we just need to add 2 more seconds. That makes it 10 seconds on the x-axis, and we know that the car decelerated to 10 meters per second, so that makes it 10 on the y-axis. And then we plot point D, and if we connect all the points together, we're gonna get this graph. So a very important you can say benefit of the speed time graph is that we can calculate distance from speed time graphs. Okay, so the distance from a speed time graph is calculated by using by calculating the area under the distance time graph. So for example, in this example we've got a speed time graph where there's an object which starts to accelerate, which starts to move with the velocity of 10 meters per second at time 5 seconds. It moves with a constant velocity of 10 meters per second for 5 seconds, and then it suddenly decelerates to 0 meters per second at the time 10 second. Now we have to calculate the area this car traveled, or this object traveled, while it was moving. So we need to calculate the area under the graph. Now this can be calculated using the formula length multiplied by width in this case, because as you can see the graph is kind of a rectangle. So for length we have to look at the x-axis because that is the length. So the car moved from 5 seconds to 10 seconds. This means that the value of L for our graph is going to be 5. Okay, and now if you look at width, we can see that the car traveled for 10 meters at the speed of 10 meters per second. So the value of W is going to be 10. So the area is equals to 10 multiplied by 5, 50 meters. 50 meters is the distance traveled by this object whilst it was moving. Okay, so next we're going to talk about how we can calculate acceleration from speed time graphs. So the connection between acceleration from a speed time graph is actually the gradient of the speed time graph is actually the acceleration of the object. So this again can be used can be calculated by using the formula of gradient delta y over delta x, where on the y-axis we have speed meters per second, this is the y-axis, and on the x-axis we have got the time. So if we plug in the units on the y-axis, as you can see that we have meters per second and on the x-axis we have seconds. So if we plug in these units and simplify, we can see that we get the final units ms minus 2, which is indeed the unit for acceleration. So we've got an example here, an example speed time graph, and we need to calculate the gradient, the acceleration for this object from point A to B. So we took point 1 as 0 0 because indeed at A the coordinate was 0 0, and then on the point 2 we took was 3 20 because this is 3 and this is 20. So B, the coordinate of B is 320. Now we just plug in the values and we can see that the acceleration is 6.67 meters per second square. This means that the object accelerated with an acceleration of 6.67 meters per second square between A and B. Now another very interesting thing that you need to know is that if we try to calculate the acceleration between C and D, you're gonna notice that the acceleration will be negative. Now why is that? Because as we can see, at C the speed was 20 meters per second and at D the speed is 10 meters per second. So the speed is decreasing. Now when the speed decreases, this we know is deceleration, and deceleration is always negative acceleration. I'm sure you're gonna stumble across many examples where you see that the acceleration is negative, and that is because they're talking about deceleration there. Okay, so the previous examples that we did with acceleration in speed time graphs was with uniform acceleration. We assumed that the acceleration was uniform. But what about non-uniform acceleration? Well, you know, the case for non-uniform acceleration is the graph for non-uniform acceleration is quite similar to the distance time graph for acceleration. So this is the speed time graph for non-uniform acceleration, and if we take a closer look at the distance time graph, for acceleration, we can see that the shape of the graphs is very close. So let's try and understand the speed time graph with non-uniform acceleration. Okay, so from A to B we can see that the line becomes steeper, the slope increases, the gradient increases, so acceleration increases. As we know from distance time graph that when the steepness or the gradient of the line increases, that shows that the velocity or speed of that object is also increasing. The same goes for speed time graph. So if you see that the steepness of a speed time graph is increasing, that is because the acceleration of that object is increasing. Okay, so for distance time graph, the increase in steepness is because the velocity is increasing, and in speed time graph, the increase in steepness of the graph is because acceleration is increasing. So we can see between A and B, the line starts to get steeper and steeper, and this steepness indicates an increase in acceleration. And at point B, we can see that the acceleration is at maximum. Then from line B to C, we can see that the line is straight. It is a constant gradient, and this indicates that the acceleration is now constant as there is no change of gradient. So from line to B, from point B to C, we can see that the acceleration is constant here. It's a straight line. Then from C to D, we can see that the steepness, the slope or the gradient of the line starts to decrease. Okay, the line starts to get flatter and flatter, and as the gradient of the line decreases, so does the acceleration. Now this is the graph for non-uniform acceleration in speed time graphs. I have a practice question here which I believe can be very helpful. So the question is, an object is accelerating along a straight horizontal track. The acceleration is uniform. This is a very important point that we need to remember. Which speed time graph represents the motion of the object? Now we know that when acceleration is uniform, we don't get curved graphs. The graphs are always a straight line. Okay, so we need to cut out C and D because these are obviously for non-uniform accelerations. These represent non-uniform accelerations. Okay, so now we're left with the option A and B. A very important thing about this question is also the first statement, that the object is accelerating along a straight horizontal track. Now this straight horizontal track tells us that the object is not changing directions. It is a constant direction because acceleration is a vector quantity, so you need to make sure that the direction is not changing. So we know that the direction is constant. Now for in B, we can see that the speed is constant, it's not changing. So if the speed isn't changing, how come we can say that the object is accelerating or decelerating? So because accelerating literally means the change in velocity per unit time. So if the speed or velocity is not changing, the object is not accelerating, which also tells us that B is not a correct option, and we can see that A is the correct option because it's a straight line, and we can see that the speed is increasing continuously. Okay, so this is the last part of this chapter, and now we're going to talk about acceleration due to gravity. Before we talk about acceleration due to gravity, let's understand gravity. So this is Earth, and this is the surface of the Earth. We know that everything on the surface of the Earth experiences a force towards the center of the Earth. This force is gravity. Okay, you guys can feel this force, me too, and this is what keeps everything on the ground. Now this force of gravity exerts acceleration. It has an acceleration, which is why if we, for example, take a bottle and let it go from mid-air, we can see that the bottle accelerates towards the earth. This acceleration is caused by gravity. Now let's talk about this acceleration. This gravitational force has a constant acceleration, and the value of that acceleration is 9.8 meters per second square. So any object on earth, any object at all, experiences this acceleration of 9.8 meters per second square. It doesn't matter if it's a feather or a heavy steel board, everything on this earth experiences the same acceleration of 9.8 meters per second square. Okay, so now you might be questioning, okay, then how come if we throw a heavy steel ball and a feather together from the same height, they don't land at the same time? Well, this is because the earth has an atmosphere which has air, and every object experiences air resistance, and this air resistance causes the difference in accelerations between different objects. But if we take a vacuum, like in this example, this diagram that I've shown, this is a heavy steel ball and a feather, and they've both been put in a vacuum, and if they let both of these objects go at the same time from the same height, and they saw that both of these landed on the ground at the same time, this is because the acceleration was constant, and the acceleration was constant because there was no air resistance which changed the acceleration. So this is a video, you can Google it yourself, like if you Google vacuum drop tests, and you'll be able to see that the acceleration of all objects is the same. The only reason that there is a difference in times that objects fall from the same height is because of air resistance, and if there is no air resistance, every object has the acceleration of 9.8 meters per second squared due to gravity. So I've got this question that we'll do, and this will further help us build our concept. Okay, so two identical objects begin to fall from rest. Okay, there's two identical objects which begin to fall from rest. One object falls from 200 meters above the Earth's surface, and the other falls from the 200 meter above the Moon's surface. So we know that the height of the objects is same. Moving on, 1 second after they have started to fall, both objects are still accelerating. Okay, there is no atmosphere on the moon, and the weight of object is constant. Which row describes the motion of both these objects? So the difference between the moon and the earth is that the earth has an atmosphere. Now the atmosphere means that every object is going to face air resistance, while on the moon there is no atmosphere, so there is no air resistance, and the acceleration remains constant. Okay, so let's keep that in mind. And they're asking us which row describes the motion of both objects at this time. This time refers to 1 second after they've started to fall. So the acceleration of the object falling of the Earth's surface. Now in the start the acceleration would have been 9.8 meters per second square, but as you know that air resistance will act on that object, and due to air resistance this acceleration will decrease. So we know that the acceleration will decrease on the Earth's surface. As for the moon, there is no atmosphere on the moon, so there is no air resistance, and the acceleration will remain constant. So the acceleration will remain constant, and our correct answer is A. I hope that made sense, and if you've got any questions, I would like you guys to ask in the comment section, and especially for this video I'd recommend that you watch it like 2 to 3 times, because these kind of concepts are a bit hard to grasp, especially the graphs, because you need to learn the concept behind these graphs. They can't just be memorized. So I'd recommend that you guys watch this video like 2-3 times if you're confused, and if you've got any confusion or anything that you can't understand because in the video, you can just leave it down in the comments and I'll answer. Thank you so much. I hope you have a great day.